Einstein is responsible for the theory of general relativity, which is a way of looking at the universe that has been proven out by observational evidence for the last 100+ years. His basic tenet is that mass warps space-time, and that this can be observed, and that as, in particular, massive objects spiral around each other, that they give out gravitational radiation or gravitational waves. This is ripples in space-time that is being caused by that mass interacting with space-time itself. So that leads to a tremendous amount of predictions. In particular, as binaries in-spiral and collide with each other, we would see these waves rise to a peak and then ripple across the universe, and that they could even be detected if we had the right kind of technology to be able to feel or see or hear space-time itself moving. Gravitational radiation astronomy is developing detectors that can actually measure that change in space-time itself. Laser interferometry. This is the best way that we can actually measure this phenomenon. In 2017, a signal that was consistent with one of these gravitational wave increases and then decreases. We call it a chirp. It gets bright and then it dies down. It looked like the prediction. But the fact that we saw a gravitational wave signal that was consistent with in-spiraling neutron stars and a kilonova as a result. A kilonova is more energetic than a nova, less energetic than a supernova. At the same time, we saw a short gamma ray burst. That was great news, and it meant that we could take all the telescopes at our disposal and quickly point them at the location of the gamma ray burst. Hubble was called into the chase. Hubble images show us a very interesting galaxy and the location of that kilonova afterglow. So Hubble was able to show us what was happening in that position, tell us how bright it was, and importantly, pinpoint the location. It's telling us where it was happening in the galaxy. And not only is that giving us information about where it was in the galactic environment, but that's also crucial information for other telescopes to be able to point to that same location, and we can take that data and combine it into that multi-wavelength picture. As laser interferometry gets more and more power behind it and it starts to see more and more of these objects, we are going to usher in the new era of multi-messenger astronomy. We're going to learn a tremendous amount about very rare events like kilonovae and other things that happen that give off gravitational waves that are going to allow us to just build more pieces onto that puzzle.